All right, welcome. In this video, we're going to go over a couple of review questions that are related to buffers. And so first, let's take a look at this one. So we've got find the pH of the following solution. So we've got a mixture of HCH2O2 and NaCHO2. What you want to recognize here when you're mixing these two things together is say, gee, those formulas look awfully similar. And so you want to recognize that this is a weak acid and its conjugate base. Because remember this, we see the sodium there, that tells you it's ionic compound. So when you stick it in water, it's going to split apart into sodium ions and then the CHO2 minus ions. And then notice how CHO2 minus, that's what you get if you take a hydrogen away from this thing right over here. So that means that this is the weak acid and this right here is a conjugate base. And whenever you mix together a weak acid plus a conjugate base, you are going to get a buffer. And if you're trying to find the pH of a buffer, there's an equation that can be useful here. Let me zoom out and look at our equation sheet. This one right here. This equation, just is just a rearrangement of this equation right here. So you could also just use a Ka expression and even an ice chart to solve this type of problem, whichever method you like, but I'm going to show using this one, which is called the Henderson-Hasselbalch Equation, to solve these types of calculations. So pH equals the pKa plus the log of the A minus over the HA. And, well, what is the Ka? Well, it tells you right here, there's a table of Ka values over to the right. So I'm going to scroll over and look at those. Whoops. And this one, HCHO2, this is formic acid. So its Ka is, let me write this over here, 1.8 times 10 to the negative fourth. And then what is pKa? If you're wondering what is that, well, that's also defined on your equation sheet. It is the negative log of the Ka, just like pH is the negative log of the H. And so the pKa is going to be the negative log of this number right here. So I'm doing this along with you on my calculator. It should be around 3 something, just to kind of check your answer for reasonableness. Let's see, 3.74. Because when you take the log of this number, your answer is going to be close to whatever this value is right here. It's going to be a little bit smaller than this number. So when I take the log of it, I get a number a little bit smaller than 4, which I did, 3.7. Cool. That's the pKa. And to find the pH, I'm going to use this equation, pH equals pKa plus log of the A minus over the HA. So my pH is going to be my pKa, which is 3.74, plus the log of my weak base, which is this one right here. So this type of calculations, you want to make sure that you are careful with keeping track of which is which. So who's my acid and who's my base here. So my base is 0.15 molar. My acid is 0.2 molar. So 0.15 divided by 0.2, I'm going to take the log of that, and I end up getting a negative number. So 3.74 minus 0.12. So I get 3.62 as my pH. So notice that when I have a buffer, my pH is going to be really similar to my pKa. And in this example, I have more of the acid component than the base. So my pH is going to be a little bit less than my pKa because I've got more acid than base present in that buffer mixture. Now let's take a look at this next one. I've got a mixture of NH3 and NH4Cl. NH4Cl, that is an ionic compound. You dissolve it in water, it's going to break apart into those ions. And NH4 looks like a weak acid, and NH3 is a weak base. So notice how you remove a hydrogen from this, you get this right here. So that's my weak conjugate acid-base pair. So again, I have a buffer. All right, so since I have a buffer, I can once again use this equation that my pH is equal to my pKa plus my log of my A minus over my HA. And if I look over here in my table, notice that, let's see, here is the pKa of ammonium is 5.6 times 10 to the negative 10. One thing I should point out is, let's say if someone did not give you the Ka of ammonium, let's say that all you had was the Kb of NH3. Let's say you knew the Kb of NH3 was 10 to the negative fifth. then you could always find the Ka using this relationship right here. Ka times Kb equals Kw. So if the Kb is 10 to the negative fifth, then the Ka would be around, 10 to the negative, 10th roughly. So anyways, just so you know, in case they don't give you the Ka, you can always use this relationship to find what you need. Ka times Kb equals Kw. What's Kw? It's this right here, 1 times 10 to the negative 14. This is all on your equation sheet. Don't need to memorize any of this one. So there we go. But this time I'm given the Ka, it's 5.6 times 10 to the negative 10. Not to do. So my pK is the negative log of 5.6 times 10 to the negative 10 plus the log of my A minus. So my A minus is the base, that's my NH3. My HA is the acid, it's the 0.22. And again, notice in this case that I have more of the acid than I do the base. So I should find that my pH is going to end up being a little bit less than my pKa. So first let's find my pKa. So 5.6 times 10 to the negative 10th. I'm going to take the log of that, so I'm going to end up with 9.25. And then if I go 0.16 divided by 0.22, take the log of that one, I end up with negative 0.14. And so when I add that, 9.25, I end up with 9.11. So again, a good way to check your answer for reasonableness. I have a little bit more of the acid than the base, so my pH should be a little bit less than my pKa. And let's see, how does a buffer work? Well, let's imagine that we took this buffer that we just made up there, and the buffer has a mixture of, it contains NH3, and it's also got some dissolved ammonium chloride. So this is what it's going to look like in the solution. That's my buffer. What's the chloride doing? Nothing. Chloride is just a spectator. It's just hanging out, not really doing anything. The reason why this works well as a buffer is if you add hydrogen ions, to your buffer, then they are going to be neutralized by your weak base. So my weak base, NH3, remember bases are hydrogen takers. So it's going to grab that hydrogen and turn it into the form of NH4. And there's already some NH4 floating around in your solution. So cool, it's not going to make a big impact on the pH. If you add a base to your buffer, then the acid component is going to be, remember acids are hydrogen givers, so my acid is going to give a hydrogen to the hydroxide and turn it into water. So now I've neutralized that hydroxide that was added. So when you have this weak acid, weak base combination present in your solution, any hydrogen that is added gets neutralized by the weak base component, and any hydroxide added gets neutralized by the weak acid component of your buffer. Here's another variation here of calculation. So I've got benzoic acid solution, and I want to make a buffer with a pH of 4.25, and I want to know how much sodium benzoate I should add. I probably need a little more room to do this one. Okay, give myself a little more space. The benzoic acid, what is it? Well, remember we've got these info off to the right here. So benzoic acid, here's the formula. It's HC7H5O2. It has a Ka of 6.5 times 10 to the negative fifth. Its conjugate base is the benzoate ion. So just take a hydrogen away, you get benzoate. There you go. And the way that you get, ions, if you wanted to add some benzoate to a mixture of benzoic acid, you need to add an ionic compound. So we're going to assume we have some sodium benzoate hanging around. So it's an ionic compound that's soluble in water because it contains sodium ions, and they're always soluble. And it also contains the benzoate ion. So when this dissolves into water, you're going to make sodium ions, and you're going to make these ions right here. Let's see, H5O2. So now you're going to have a buffer because you're going to have a weak acid and its conjugate base. All right, so let's look at what we know. We know we've got this equation, pH equals pKa plus the log of A minus over HA. We know what we want our pH to be is 4.25. Okay, the pKa, we haven't calculated it yet, but we could figure it out. Let's take the negative log. So 6.5 E5 negative take the negative log of it. My pKa is 4.19. So notice how I want my pH to be a little bit higher than my pKa. So I'm going to stop and just notice that and say, okay, my final answer, I'm going to expect to have a higher concentration of base than acid. Okay. So that's going to be the log of my base concentration, which I don't know, but my acid concentration I do know. It's 0.2 molar. You should notice this is a very similar calculation to like when we did in the lab. We're trying to design a buffer with a certain pH. So I'm going to rearrange. So 4.25 minus 4.19. So I'm going to subtract 4.19 from both sides. I get 0.06 equals the log of A minus over 0.2. So to isolate this, I'm going to do the inverse of a log is to go 10 to the power up. So 10 to the 0.06 equals A minus over 0.2. Again, I need more space here. I'm going to keep adding more space. There we go. And 10 to the 0.06. You might think that's not a big deal, but you know, it's exponential. So that is 1.15 equals your A minus concentration over 0.2. So to find your A minus concentration, it's going to be 1.15 times 0.2 molar. And so that ends up being 0.23 molar. So notice how to get our buffer with this pH, we want our base component to be a little bit more concentrated than our acid. So we've got 0.2 molar acid, but 0.23 molar base, which fits with what we were observing because the pH will be a little higher than our pKa. All right. I still haven't answered the question, though. The question is what mass of sodium benzoate we should use. And so we know the molarity and we know the volume. So molarity times our liters will tell us how many moles. 0.5. So we need 0.0. I think we just have 2 sig figs. Yep, 0.034 moles of sodium benzoate. And then this is sodium benzoate, so I have to take a moment to find the molar mass, oh no, of this substance. Hold on, I'm gonna pause for a moment. Okay, here we go. So the molar mass of this substance is 144 grams per mole. You use your periodic table, or if we want to be a little lazy at home, we can Google it. So that's our molar mass. And so to figure out how many grams, it's 0.034 moles of sodium benzoate, and it's 144 grams per mole. So what I'm going to do is I'm going to multiply that by 144. Boom. And it looks like I need 4.96. So I think if I'm rounded 2 sig figs, I guess that's 5.0 grams. So if I was going to make this buffer, what I would do is I would have, 150 milliliters of 0.2 molar benzoic acid. That's already measured out there, right? And then I'm going to come along, I'm going to add 5 grams of sodium benzoate. So my solution already contains the weak acid, and my solid contains the conjugate base. And so I'm going to dissolve this into this solution. Now I've got a buffer that contains both the weak acid and the conjugate base. So again, this is very similar to our design a buffer lab kind of calculation that we did. And then down here, this is a matter of kind of picking out which components would be best to make a buffer with a certain pH. So we want a buffer of a pH of 7.2. The rules are to have a good buffer, we want to make sure that they are a weak acid-base conjugate pair. And the pH that we want should be close to the pKa of your acid. So let's see, which ones have a pKa close to 7? Well, it looks like this one will, and I think that's about it. So HClO is a weak acid that has a pKa close to 7, because I can tell just from looking at its exponent is 8, so that's close to 7. And so it looks like this right here would be a good buffer because you have your HClO and then your KClO. When you stick it in water, it's going to break apart into these 2 ions. So there you go. There's my weak acid and its conjugate base. All right, same thing down here. Looking for a weak acid-base pair where the pH is close to the pKa. So let's scan through these given Ka values. And let's see, this one's going to have a pKa close to 9. So will this one down here. So I got to look on my list and see what options I have. Well, it looks like this one is our best option. So we got NH3 and some, ammonium chloride. The chloride is just going to be a spectator. So this is our buffer, NH3 and NH4+. And NH4+ has a pKa that is around 9-ish, right? It's going to be, because its exponent is 10. So be between 9 and 10. Cool. And then here's a kind of last set here to think through this idea of, does pH equal to pKa, or is it greater than pKa or less than the pKa? So a reminder, if you have exactly equal amounts of your weak acid and your conjugate base, the pH will be exactly equal to the pKa. If you have a little bit more acid in the base, then the pH is going to be less, more acidic. That makes sense. If you have a little bit more of the base component than the acid, then it's going to be a little bit more basic. So the pH is going to be greater than the pKa. So let's look at this first one. We've got 0.1 moles of acid and 0.05 moles of its conjugate base. So it looks like our amount of acid is greater than the amount of the conjugate base. Therefore, my pH is going to be less than my pKa. So like if the pKa is, 9, my pH might be 8.5, right? All right, how about this one? In this case, you have 0.1 moles of HA and 0.15 moles of A-. So in this case, my A- is greater than my HA. So my pH, I've got more base than acid, so my pH is going to be greater than the pKa. It's going to be a little more basic. This one, if I got 0.1 mole of HA and 0.05 moles of OH-, this looks like a titration scenario. So what that means here is I start with HA, I'm adding some hydroxide. I'm actually going to write this out real quick. And you don't necessarily have to, but I am going to, my hydroxide is going to react. And as it reacts, it's going to use up some of my HA here. So I got 0.1 and I got half as much base. So what that means is half of my acid is going to react and it is going to turn into A-. So my base gets all used up. And after they react, I'm going to have 0.05 moles of acid, and I'm going to have 0.05 moles of this conjugate base. What we have done here is we have just titrated something to the half equivalence point. If you want to connect this back to a titration curve, it's like you're titrating your acid, and you stopped right here at the half equivalence point. At this point, your amount of HA and your A- are going to be equal. So at that point, your pH is going to equal your pKa. And then this last one would be if I have 0.1 mole of HA and I added 0.075 moles of hydroxide. So let's actually look back at this titration curve again. That would be if instead of stopping at the half equivalence point, you went a little bit further and made even more base. So in this case, you'd have more of the conjugate base present than the acid. So your pH would be greater than your pKa. Okay. That's it. Hope this helps. Thanks for watching.